and today we are presenting our AI-powered education assistant designed to help students from raw study material to meaningful learning resources. So in the education domain, students often work with different types of content such as textbook chapters, lecture notes, handwritten notes, and images of the study materials. So extracting useful insights from this information, it can be time consuming. And our solution addresses this challenge by allowing students to interact with content through both text and images. So to achieve this, we have combined two major areas of the artificial intelligence, which is NLP and computer vision. So NLP for the tasks such as question answering or the text summarization, and the computer vision for image classifications. So from architectural perspective, this application follows a modular design. For the AI, at the backend, we have used FastAPI. For the front end, we have used Gradio, and data we have pulled from the Hugging Face. UI interface is organized into separate tabs over here, and each tab representing a specific capability of the system, providing intuitive and interactive user experience for the students. In the coming section of the demo, my group members will first showcase the NLP capabilities, and then we'll move on to the CV features. And finally, we'll demonstrate the fine-tuned model comparison of matrix dashboard. So over to you, Sonam.
Thanks, Vrunda. So the first feature is Ask a Question, which uses the DeepSet Roberta-based Squad 2 model. This is an extractive question answering model fine-tuned on Squad 2.0 dataset. Click on answer, please. So the model does not generate a new answer. Instead, it extracts the most relevant answer directly from the provided text. Along with the answer, it displays confidence score and the inference latency, indicating how quickly the prediction was made. So the next feature is text summarization. It is powered by Facebook BART large CNN model. So a BART model is fine-tuned on CNN Daily Mail dataset, and this is an abstractive summarization model, meaning it rewrites the content in a shorter form using its own words while preserving the key information. So the third feature is quiz generation, which uses Google's FLAN T5 base model. So in multi-question mode, the passage is divided into smaller sentence chunks, and the model generates one question for each chunk. In single mode, the complete passage is provided as one prompt, and the model generates the requested number of quiz questions together. So the output also shows which model was used to generate the questions. So the fourth feature is topic classification, which uses Facebook's BART large MNLI model. This model performs zero-shot text classification, meaning it can classify text into predefined categories without being specifically trained on these categories. So the model predicts whether the text belongs to categories such as physics, chemistry, biology, or other, along with the confidence score for each category. Handing over to Adarsh for computer vision task.
Hi Sonam, thank you so much. Hi Vrinda, thanks. So I will explain the next part, that is computer vision model. So in computer vision, we have used zero-shot image classification, and here we have used two-step pipeline. So yeah, so in this particular zero-shot image classification, we have implemented OpenAI Clip VIT based patch 32, a pre-trained model that is based on the architecture of base Bayesian transformer bit B32, and that is capable of processing the image by 32 cross 32 pixel patches, and also it is enabled with text encoder, which is using the mask self attention along with the transformer to parses the text sequence, and as I said, zero shot classification, meaning that it will upload the images of student can upload the image, and then model will classify into 4 categories, and then we have also like 4 categories are like uh, our it can be diagram, it can be equation, it can be chart or text pages. So a second part of this architecture is OCR with EasyOCR. So the library we have used here, EasyOCR, to processing of the those data input from the image, and then it can do some adjustment on the resolution, contrast enhancement, and also resizing, and if any rotation fix required to exactly the uh, get the meaning and the particular semantic sense of that written text in the image. And then once we click on analyze button, as we can see here, it can quickly give the results into the along with their percentage of the classification. Like if chart is 61% here we can see, meaning that it is like classifying as a chart, uh, being higher probability, and then it will also predict the OCR text. So yeah, thank you. Over to Anas.
Yeah, thanks, Adarsh. So let's move to the next step here, the fine-tuned. So for this, in this step, we compare a base model against a fine-tuned model on our domain dataset. So the base model is Google Flantify base we used here, and against it we compare a model fine-tuned specifically on the SciQ dataset, and it is the adapter called LoRa here. So if this adapter isn't available, the app falls back to the base model, and which is fine-tuned for generative question answering. So let's run a sample question here, which my teammate already given here. So when we compare, when we click on the compare models, so let's wait for the result. Yeah, it came. So you can see here both the answers side by side, the base model and the science sci-fi SciQ fine-tuned model answers are displaying here with the latencies. So beyond this live comparison, we also built an offline evaluation script. Okay, so I would request if we can quickly move to the Visual Studio to go through the code part. Yeah, if we go to the evaluation IQ, yep. So this is the background of the uh, interface what we have seen just now. So this runs both the models over a batch of samples from the actual LNAI IQ validation sets and scores them using token I label F1 and exact match against the ground truth answers. So that's all about the fine-tuned. Can we move to the interface again and the final tab matrices here? Okay. So here in the matrix, okay, if we click on the refresh matrices, after that we can see the total request, error rate, P50, P95 latency, a breakdown of how many calls hit each endpoint and which underlying models were used, all captured automatically by our matrix middleware and on every request. So I would request Aman to go through the code part and conclude.
Okay.
Thanks, everyone.
Thanks, Anas. Yeah, thanks everyone. Let me give you a brief of the coding part over here. So for the front end, we are basically using the Gradio app, and it is basically whatever the UI that you are seeing over here is just basically coming out through this Gradio app. So here, Gradio is basically a front end library in Python, so we don't have to write the HTML or the CSS part from the scratch. Just using the normal Python functions, we can create such UI within an easy phase. Moving to the next part of this, for the backend we have used the FastAPI, and all the routes has been created over here. As you can see, I have opened two terminals over here. One is for the backend for the FastAPI, and the another one is for the Gradio UI. And if we open up the Open API Swagger page, you can see the each individual request page for what is their respective schema and how they are being generated the text from that. So all the queries are being sent using a specific JSON structure. Based on this, the query data gets sent to a specific URL, and based on that we get the response from the model. For here, for loading the model, we have just used the lazy loading, so we don't have to download the model for each run. We have stored the data in our cache memory, so the model will be loaded in a one time, and once we hit again and again for the prediction part, it will not need to download it again and again. So this is how the complete task has been working over here. Then we have the respective services, as Sonam and others and Brenda and other team members like Anas have worked their respective part. We have created different services for NLP and the other respective tasks, and with respect to the models, we have created this models.yml file so that for each individual model the respective model can be chosen in a right way. And in the end we have the matrices.py that basically calculates the each endpoint call time, basically what is their latency, which model is being used, and how many times a respective URL has been called. And this is how the complete workflow done. So the Gradio app basically runs the UI, then the FastAPI connects the URLs, and their respective models are being cached into the memory. The request goes in and we get the prediction over output. So these are the output based on the terminals. These are the Gradio terminals output, and this is how our project is working along. So this was the complete demonstration of our group assignment. Thanks everyone.
So as a wrap up, if we conclude about this project, okay, so this project combines multiple NLP and computer vision models behind a single FastAPI service with a concrete fine-tuned versus base comparison on our domain datasets and built-in latency and error monitoring. So thank you team for your efforts and dedication in closing this project successfully. Thanks a lot.
Thank you team.
Thank you.
Yeah, thanks.
Thank you. Bye.
Bye.